So today, we're going to dive into two really powerful tools for building smarter predictive models: Ridge and Lasso Regression. You've probably heard that saying, less is more. Well, we're about to see why that's an absolutely game-changing idea in machine learning.
And that really gets to the heart of it, right? What if this secret to making better, more accurate predictions isn't about adding more and more complexity, but about strategically taking it away? I know it sounds a little backward, but this is the core idea that makes these techniques so incredibly useful.
All right, so let's start with the basics. Standard linear regression is a fantastic workhorse. We all use it, but it can run into some serious trouble, especially when you throw complex data at it. Let's take a look at two of its biggest weaknesses. So check this out. This is the classic problem of overfitting. Over on the left, you see the model has learned the training data perfectly. It's even memorized the random noise and the little quirks. But then on the right, the moment you show it new data it hasn't seen before, it just falls apart. It's like a student who only memorizes the answers for a test but never actually learns the concepts. They can't solve a new problem to save their life.
And then there's this other headache, multicollinearity. This is just a fancy word for when your input variables are highly related to each other. Imagine you're predicting house prices using both square footage and the number of bedrooms. Well, those two are obviously linked, right? The model gets confused about which one is actually driving the price, and the results can get really shaky and hard to trust.
So, how do we fight back against these problems? How do we stop our models from getting too complicated? Well, the answer is this brilliant technique called regularization. And trust me, this is our secret weapon for building simpler, much more robust models. At its core, regularization works by adding a penalty for being too complex. It's like telling the model, hey, I absolutely want you to fit the data well, but I'm also going to penalize you if your parameters get too big and out of control. It basically forces the model to find a simpler, more elegant solution. Think about a standard linear regression model. It's got one job and one job only: minimize the error. That's the difference between what it predicts and what the actual values are. This total error is called the residual sum of squares, or RSS. The model is just laser-focused on being as accurate as possible on the data it was trained on. But regularization completely changes the game. It introduces a new goal. Now the model has to minimize the error plus this new penalty term that's based on how big its coefficients are. And that is the whole point. It creates this trade-off. The model has to find a balance between fitting the data perfectly and keeping its own complexity in check. All right, so let's get practical and see how this works, starting with our first method, ridge regression. Ridge uses something called an L2 penalty to kind of rein in those unruly model coefficients. Okay, so here's the ridge formula. We're still trying to minimize the error, the RSS, but look at that new term we added. That little lambda symbol is like a tuning knob. It lets us decide how much we care about the penalty. But the key part here is that we're adding up the square of the coefficients. Squaring them means that really big coefficients get penalized way more than small ones. It's a powerful way to force the model to shrink them down.
And what does all that math actually do? Well, this is the core effect of ridge: shrinkage. It pulls all the coefficients down, shrinking them towards zero and reducing their impact. But the key word here is towards. Ridge is like a gentle nudge. It makes the coefficients really small, but it almost never pushes them all the way to exactly zero.
So, why would you reach for ridge? Well, it's fantastic for dealing with that multicollinearity problem we talked about. By shrinking down those correlated coefficients, it makes the whole model much more stable. You get to keep all of your original features in the mix, you just reduce their overall influence.
Now for our second tool, which, let's just say, takes a much more aggressive approach. Meet lasso regression. It uses what's called an L1 penalty. And lasso, fun fact, actually stands for least absolute shrinkage and selection operator, which pretty much tells you everything you need to know about what it does. The lasso formula looks almost identical to ridge, but there is one critical change. See that? Instead of squaring the coefficients, we're now adding a penalty based on their absolute value. Now, this might seem like a really minor tweak, but the different mathematical shape of this penalty is what allows lasso to do something truly special that ridge just can't. And here it is, the magic of lasso. That L1 penalty has the power to shrink some coefficients not just towards zero, but all the way to zero. And when a coefficient becomes zero, its feature is, for all practical purposes, completely removed from the model. So, lasso doesn't just tame your features, it performs automatic feature selection.
This makes Lasso an incredibly powerful tool. If you've got a dataset with hundreds, maybe thousands of features, and you have a hunch that a lot of them are just noise, Lasso is your go-to. It automatically cleans house, kicking out the useless predictors and leaving you with a much simpler, easier-to-understand model.
Okay, enough theory. We've talked it through, now let's actually see what this looks like. This is where the difference between Ridge and Lasso really comes to life.
So here it is, the showdown. On the left, we have Ridge, the shrinker, and on the right, we have Lasso, the selector. Let's see how each one of them handles the exact same starting model.
Okay, so let's start with a basic model that has 5 features. The height of each bar represents its coefficient, basically how much importance the model gives it. You can see feature 2 has a big positive impact, while feature 4 has a strong negative one. This is our baseline before any regularization.
Now we apply Ridge. See what happened? Every single bar got shorter. Each coefficient has been shrunk down towards 0. Their influence has been dialed back. But, and this is crucial, all 5 features are still in the model. Nothing has been totally removed.
And now Lasso. Look at that. This is the magic right here. Features 1, 3, and 5 have been completely zeroed out. Their bars are totally flat. Lasso has looked at the data and decided, you know what? These 3 aren't important, and it has automatically kicked them out of the model, leaving us with a much simpler model that only relies on features 2 and 4. That is feature selection in action.
So, we've got these 2 incredibly powerful tools. The big question is, how do you decide which one to use for your particular problem?
Here's a simple cheat sheet to help you out. If you're using the L2 penalty, that's Ridge. It only shrinks coefficients, and it's your best bet when you have a lot of correlated features and you think they're all probably important. But if you're using the L1 penalty, that's Lasso. It both shrinks and selects, and it's the perfect tool when you think many of your features are just noise and you want a simpler, more interpretable model. And that leaves us with one final thought to chew on. Imagine you were just handed a dataset with 1,000 different features, 1,000 potential predictors. Where would you even start? If your main goal is to cut through all that noise, find the handful of variables that truly matter, and build the simplest possible model, which tool are you reaching for first?